Okay, we're back for our Unit 3 free response rubric. So here we've got a ball that's being dropped from a height of 5 meters, and and then it undergoes a perfectly elastic collision with the ground, rebounds. The instant the ball rebounds, a small blob of clay is released from also 5 meters directly above the ball. The clay blob is descending, collides with the ball, which is ascending. Gravity we're going to use as 10. Air resistance is going to be negligible, and the collision time is also negligible. So we need to do a couple of determinations. The speed of the ball immediately after it hits the ground, the time after the release of the clay blob when the collision takes place, the height at which the collision takes place, and the speeds of the ball and the clay blob immediately after the collision, and then the magnitude and direction of their velocity after the collision, assuming they stick together. So let's look through the rubric for this free response. And our Unit 2 was from 1979. This one's from 1992. Still a little on the older side, but getting more recent, so a little more like what you would see today. So again, as I stated in our Unit 2 free response, whenever there is conservation of energy, make some type of statement for that. So here they have either of these equations could be used because both show conservation of energy, and that earns you 1 point. So we know that the velocity with which the ball hits the ground is going to be related to the initial potential energy that it has, because energy is conserved. So we can solve for V, and we can plug in our numbers, and so we find V is 10 meters per second if you use G equals 10. If you use G equals 9.8, then your velocity is going to be 9.9 meters per second. They did accept both, even though the question said use 10. So finding the correct velocity also got you a point. Then we move to part B, and we need the time at which the clay is released. So you have to have some indication that, oh, I'm sorry, this is for the time when the collision takes place. So you have to have some indication that the height of the clay and the height of the ball are the same when the collision takes place. Okay? So we know for the ball, it is coming back up. It has some initial velocity as it leaves the ground, okay? And it's going to be slowing down on its way up because gravity is acting in the opposite direction. So therefore, we can use a kinematic equation that has constant velocity, which is that the height of the ball is going to equal its initial velocity upward, so it's positive, times time, minus 1/2, and in this case your acceleration is g t squared, and minus because it's in the opposite direction for the acceleration. Okay? For the clay, it has no initial velocity, but it has initial height, and it's accelerating downward. And we've already used up as positive in the first equation, so that's why we have our initial height minus 1/2 gt squared. So because the height of the ball and the height of the clay are going to be the same at the time of collision, you can set the two equations equal to each other and solve for t. And so you see that you got a point for the ball equation, a point for the clay equation, and then setting them equal to each other and solving correctly gets you a point. If you use G equals 10, T is then 0.5. If you used 9.8, T is 0.51 seconds. Okay, so now that gives you the time that the collision took place. Now we want to know the height at which the collision took place. So we're going to take that time and substitute it back in to our equation. So just substituting that in gets you a point, and then the answer also gets you a point. So again, always show your work. Show what your equation you're using, show what you substitute into the equation. if you show the equation before you substitute, that's always the best practice because that makes it easiest for the reader to follow. The easier time the reader has following your work, the more points they're likely to give you. Now, you could have also substituted it into the ball equation instead of the clay equation. It didn't matter which one you used. Then we want to find the speed of the ball right before the collision and the speed of the clay right before the collision. So again, we can use kinematic equations that have constant velocity. For the ball, it's got an initial velocity upward and it's slowing down. So V initial minus G times T will give you the speed of the ball. For the clay, it has no initial velocity and it's falling, so just G times T. And you can see equation got you a point, answer got you a point for the ball. And what's interesting here for the clay is that you only got the point for the answer. But ultimately, they do want to see the work. Then, for part D, or E, where we're finding the speed of the clay ball system, any statement whatsoever for conservation momentum gets a point. So even just writing out in words, momentum is conserved, will get you a point. Writing P initial equals P final or P naught equals P final gets you a point. Writing out the equation full out like they have here, the MBVB minus MCVC equals the sum of the masses times the final velocity. That also counts for that statement of conservation momentum. So that just writing that statement alone would get you the point for the statement plus the point for the conservation momentum. Then solving for the correct velocity gets you a point. And you also had to note the direction to get the final point, or it had to be obvious from the notation that it's positive, therefore it must be upward. If you're ever in doubt, overstate things. It never hurts. Okay, so those are your 15 points from the Unit 3 free response question.